So I'm Guido Chari, and I will present my work titled Towards Fully Reflective Environments. It's a work joined with Diego Arbebetsky, Stefan Mara, and Stefan Dukas. And I will start presenting briefly the main concepts for framing correctly our approach, our contribution. The first one is this concept of live programming, and this is a very general concept. But we are mainly interested in this property of perceiving instantaneously the effects of the change we made to the system. And in particular, we are interested in this idea of reducing the conceptual gap that may be produced by the thing that the mind may fly to another place when one has to wait for the compilation step. The second related concept, quite related with live programming, is this idea of reflection. And essentially, reflection in computer language, in programming languages, is this idea of being able to observe or adapt the behavior or the structure of programs themselves. And there are a lot of programming languages, from historical ones to modern ones, that include different degrees of reflective capabilities. The last concept I will introduce is this we name execution environments, and most of you here may know as virtual machines for programming languages. They are usually very complex software artifacts responsible for executing, giving semantics, and organizing the memory of the programs. And as a common denominator, they are usually very complex, and they have a lot of low-level components that are quite intertwined and coupled between them. And last but not least, the performance is crucial because the performance of the programs, or even of the programming languages, strongly depends on the performance of this component. So to summarize and try to introduce the problem we want to tackle, we have a lot of programming languages. A considerable amount of these programming languages provide live techniques, and a lot of these, or usually these live techniques, are implemented in top of reflective APIs. And these dynamic languages run in top of very complex execution environments. What we see, what we identify as a problem, is there is usually a very limited interaction between the execution environment and the programs at runtime. And usually, to be more clear, there is a possible interaction, but it's only one way. So the virtual machine must know or must interact with the program for executing it, but the program sees the virtual machine as a black box and cannot adapt or interact with it. And our proposal mainly is to bridge the gap between these two worlds, between the dynamic programming languages or the dynamic application and the static virtual machine, providing a two-way communication. And many of you may be wondering why we would like to have a two-way communication between these two worlds. And well, we have thought and we have experimented with a couple of scenarios. In the first, on the one hand, one could ask why developers may work in very dynamic environments, but VM developers work in very static environments. So providing reflective or this two-way communication may provide better tools and better experience for these VM developers. But we are thinking of broader applications of having this two-way communication. And one of the problems we have experimented was this of unanticipated adaptation scenarios, when programs that must still be running or that must not be shut down need to adapt to changes that the developers could not anticipate. For example, developers need to change at runtime the object layout for having more efficient memory layouts, or providing immutability to a couple of objects at runtime for providing some security property, implementing transparent proxies for distributing our application while it is running. And all these scenarios could generalize to any kind of scenarios where we can think on flexible of having a language or an environment, a programming environment that has flexible semantics. For example, for implementing new language filters while the system is running, experimenting with execution traces, and last but not least, I have seen a lot of talks in this week. So we think that it will also be very important for optimization. So the programs may communicate with the virtual machine, so the virtual machine may tailor better its optimizations. And since we think there are not many, or even there are very few approaches that provides this two-way communication, we think there will be many more use cases in the future. So how is the way we think or we approach or we tackle this problem of providing this two-way communication is what we call reflective execution environments. So reflective environments are those that, as I introduced, provide reflective capabilities for introspecting or interceding the behavior or the structure of programs. We introduce a new dimension that is the separation of the application for reflection for the application or for the virtual machine. And we are interested mainly in what are the consequences of incorporating reflective capabilities for the virtual machine in terms of feasibility and also in terms of applicability. So we start by designing or defining what reflective virtual machines should be or the properties they should promote besides its definition. And the first one for us, the first maxim, is that reflective virtual machines should provide universal reflection. So this means that every entity of the system, both from the virtual machine or from the programming language or the application, must provide reflective capabilities, intercession and introspection reflective capabilities. The second maxim says mainly that we must introduce reflective capabilities for the VM level, but we must not increase the complexity of the language, at least not exponentially. So if there are already abstractions for dealing with reflection at the application level, we must try to reuse the same abstractions for dealing with reflection at the execution environment level. And the last maxim, the third one, says mainly that even though we must try to reuse the same abstractions, these abstractions must allow us to work with reflection, to deal with reflection at different levels and independently. We must not deal with reflection at the programming language level or at the application level if we want to do changes or adaptations at the virtual machine levels. We must have like a separation of concerns. So I already introduced what is our approach. I already introduced the maxims we define for tackling this idea of reflective execution environments. And now I will introduce you what we do. We went mainly for an empirical approach that consists of selecting some concrete problem we want to tackle with reflective capabilities at the virtual machine level, implement prototypes that fulfill this problem, then analyze the results, mainly the reflective results of these prototypes, and then feedback these reflective results and go for an iterative approach and start implementing more prototypes for incorporating even more and more reflective capabilities. And I will show you now the first iteration, our first iteration, or at least the mature version of our first iteration. But first, I want to introduce you the reference architecture we define for analyzing and comparing the different eventual prototypes. So all the prototypes must in some way comply with this architecture, the same architecture. And the architecture is mainly a research approach architecture, very minimal. It only is conformed by the essential entities for running any object-oriented programming, any object-oriented program in a very pure way. It just deals with objects and methods. And the most salient or distinct issue or thing of this architecture is that it says that there must be any system complying with this architecture must have two different meta-object protocols. One at the application level or for dealing with reflection at the application level, and another independent one for dealing with execution environment or the virtual machine reflection at the virtual machine level. And now, the result of our first iteration, we essentially implement a very prototypical but complete virtual machine that is written in Smalltalk, and it is also it runs Smalltalk programs. It's a metacircular prototypical VM, and its main distinction feature is that it promotes, it has honoring the reference architecture, meta-object protocol. Essentially, this meta-object protocol has one meta-class for each component of the architecture that we have identified. It is from the VM level. And the sum of all the operations of each of these components conforms what is, for us, all the reflective capabilities of this Mate version 1. Then we start analyzing the results of our first prototype, and we compare it mainly with the two related works we identified. There are very few works in the field promoting reflective capabilities at the virtual machine level. And what we can see is that our prototype is mainly very competitive in all of the components if we analyze them independently, but it's the only one considering reflection as a whole, reflection as an integral thing, reflection at the VM level as a whole as an integral thing of the system. And it is worth noting that we are on an ongoing work. We want to implement more prototypes, and our long-term research goal is to find what are the limits of incorporating reflection at the virtual machine level on each of the components we have identified, and also what are the consequences or the possible interferences of implementing or incorporating more operations on each of the components. What is the eventual interference with incorporating reflection operations on other components. Finally, the problem we selected for analyzing our prototype was the unanticipated fine-grained adaptation scenarios, the idea of changing the system at runtime in a very fine-grained manner. And this is a code snippet illustrating how easy it is to change the system with this meta-object protocol. Essentially, here in the first lines, there is a class, immutable class, that subclass the executor meta-class of the meta-object protocol and just redefines the store field operation, so it throws an immutable exception. And then the other lines are just a little script for installing this meta-object or an instance of this meta-class in a predefined set of objects that we call critical data. And with this, we can ensure that after installing this meta-object to this set of objects, the system ensures that the semantic now is immutable for this set of objects. And the main distinction of this feature is that we can do this all at runtime without shutting down the system. And you can go and read the paper, see in the paper. If you want more details, we showcase a lot of different scenarios and anticipated adaptation scenarios in the paper. And for concluding, essentially with this first prototype, we work mainly on the feasibility issues of having a reflective execution environment besides having some definitions. We also demonstrate that this approach is quite useful and profitable in a lot of use cases, in a lot of scenarios when you have to adapt the system at runtime. And now we are already working on porting all our infrastructure to the Truffle Graal framework, language framework infrastructure, so we can start experimenting optimizations tailored to this kind of reflective environments or our reflective operations. And I think that's all I have to say. Thank you very much, and I will be glad to answer any question.